After years of research and development of clean consumption technologies, LEENA Laboratories is sponsoring the LEENA Forum. The Low Energy Edge Node Analytic Forum, or LEENA Forum, will be a California-based 501c6 mutual benefit corporation, with membership that includes a wide range of leaders in the energy value chain. Leaders committed to solving the energy crisis by focusing on the balance between clean energy supply and clean energy demand. On the supply side, the energy industry, utilities, federal, state, and local governments all spend billions of dollars each year optimizing centralized energy production and distribution. This is a complex system of systems that require extensive and expensive resources and complex government oversight. On the demand side, energy consumption is usually represented as a very simple scalar quantity. That is the energy we, as consumers, need to live our lives. And we're reassured by utilities and government agencies the answer to eliminating the energy crisis is investment in centralized utilities funded to replace quad-for-quad carbon-based energy with a wide range of clean energy technologies. Membership of the Forum also strongly believes investment in clean energy technologies is an important part of our energy future. But we also know it is not, on its own, the answer to the energy crisis. We believe clean consumption technologies that eliminate energy waste are equally important and necessary to provide a sustainable, low-cost, clean energy future. To put things in the proper perspective, take a minute and read the cartoon and consider what your reaction to this situation would be. Clearly, a better approach to become healthy is to reduce your calorie intake by 60% and consume healthy food. Regardless of what you eat, consuming 5,000 calories per day is unhealthy. But when it comes to our environmental health, we seem to react differently. Take a minute and consider what your reaction would be in this situation. Why do we fail to apply the same common sense to an environmental health crisis that we apply to a personal health crisis? You may be skeptical that you can maintain your lifestyle consuming just 4 megawatt hours of electricity per year. But the fact is you already do. In fact, the amount of electricity consumed by the average residents in the United States each year to do useful work is less than 2 megawatt hours. The remaining 8 megawatt hours is energy waste. The rest of this presentation on the forum covers who we are and why we are so focused on research and development of clean consumption technologies. Members of the forum are leaders in the energy value chain. We are teachers, researchers, scientists, engineers, inventors, designers, business professionals, manufacturers, retailers, investors, and regulators that believe we have solutions that eliminate the energy crisis, reduce energy costs, and end the harm caused by harvesting energy from the earth. Even more importantly, we're consumers that understand the value proposition of energy efficiency. We know the cleanest energy is not the energy that needs to be harvested, transported, or burned. It is the energy we don't consume. The concept of the LEENA Forum evolved naturally from years of research in energy efficiency conducted by LEENA Laboratories. The role of the forum is to support innovations that lead to commercialization of clean consumption technologies and the LEENA architectures, providing consumers real choice in energy efficiency in products and services. Our research also led to the realization that we have a problem, a complete lack of understanding of energy efficiency and the important role it plays in a comprehensive solution to our energy crisis. The challenge we face in commercialization of clean consumption technologies is that, similar to the development of cellular technologies, development of clean consumption technologies requires concurrent development of both infrastructure and smart edge node devices. This requires extensive collaboration between development partners to coordinate activities. The forum incubates and enables disruptive innovations that drive a balance between clean energy technology and clean consumption technologies. The forum provides a unique perspective, leadership, partnerships, and a strong history of development of innovative solutions to solve difficult problems. This is a critical time for both industrialized and non-industrialized societies to choose better when consuming natural resources and understand how to utilize technology to benefit themselves and all life on this planet. This presentation includes a simple introduction to energy modeling. In compelling results that illustrate how a simple shift in our thinking and understanding of the energy crisis can lead to real solutions. We base our analytic models on the Energy Information Administration's AEO 2018 report and NEMS models that include projected energy production and consumption through 2050. This provides a platform to evaluate the impact of the LEENA architectures on these projections and on our energy future. The AEO 2018 report includes dozens of scenarios that provide projections based on the impact of macroeconomic variables such as economic growth, population, cost of fuel, impact of government policies and regulation, assessment of fees and tariffs on energy sources, as well as industry and government investment in clean energy technologies. EIA is the gold standard for energy research and the most widely used analytic platform for local, state, and national governments to formulate energy policy and develop regulations. The National Energy Modeling System, or NEMS, is the underlying analytic structure used by EIA to model our energy future. LEENA architectures include innovations that substantially modify electricity demand load curves, resulting in dramatically lower demand from centralized grid-based distribution systems. The EIA reference case provides an excellent baseline for evaluating the expected behavior and trade space of energy supply and demand. It is based on the most likely macroeconomic, technology, policy, and regulatory factors. Dozens of side cases include analysis by EIA highlighting the impact of variations to the reference case, and our analysis of the impact of the LEENA case is, like other side cases, based on the reference case. In addition to the reference case, we include EIA analysis of the $25 carbon allowance fee case and the new efficiency requirements case. The $25 carbon allowance fee case is included because it is the most aggressive EIA side case focused on reduction of greenhouse gas equivalent CO2 emissions. The new efficiency requirements case represents how aggressive energy efficiency requirements that are not based on clean consumption technologies impact our energy future. These requirements are based on the Energy Star program. A simple way to understand the value of energy efficiency is to represent the relationship between energy supply and demand as a simple balance beam. In an ideal world, we achieve balance when the fulcrum, the point at which the balance beam rests and pivots, is at the center of the beam and equal amounts of mass are suspended on each leg of the beam, much like a teeter-totter. In an ideal world, the energy harvested from the earth is delivered to consumers to do useful work. But we don't live in an ideal world. According to EIA data, in 2017, this is what the balance between energy harvested from the earth and energy delivered to customers look like. You may notice the fulcrum in our balance being moved because we harvest 3 times as much energy from the earth than we deliver to customers. The size of the ball that represents the energy we harvest has also tripled and is primarily black to indicate over 80% of the energy harvested came from carbon-based fuels. The atmosphere of the earth is also contaminated with byproducts of energy production. In 2017, in the United States, we harvested 37.25 quads of energy from the earth, but only delivered 12.67 quads to consumers. So the energy efficiency of our utility-based centralized electric grid in the United States was 33.7%. Over the past 50 years, as concern with harm caused by harvesting energy from the earth increased, we began replacing carbon-based energy with renewable energy such as wind, solar, hydraulic, geothermal, and biomass. In 2017, 17.1% of the total production of electricity was from renewable energy sources. So, most of the energy harvested from the Earth came from carbon-based sources, releasing 1.76 billion metric tons of greenhouse gas equivalent CO2 pollution into the atmosphere. Next, let's look at the EIA reference case projections for 2050. This is a bit disappointing. This slide represents the reference case, with expected improvements in energy technology, supply, production, consumption, policy, and regulatory updates by 2050. Although we do see improvements in overall energy efficiency increasing from 33.7% to just over 37%, we also see the amount of energy harvested from the Earth increasing from 37.25 quads to over 40 quads in 2050. This is due to increased demand by consumers, based on population growth, migration patterns, and other macroeconomic factors. Consumption increases from 12.67 to over 15 quads in 2050. A possible bit of good news is the energy from renewable sources increased from 691 billion kilowatt hours to 1,651 billion kilowatt hours. Unfortunately, in 2050, demand also increased from 4,042 billion kilowatt hours to 5,255 billion kilowatt hours. So, in 2050, more than two-thirds of production of all electricity will continue to be from carbon-based fuels. Another possible bit of good news is, despite a substantial increase in harvested energy, the amount of greenhouse gas equivalent CO2 pollution decreased from 1.76 billion metric tons in 2017 to just 1.52 billion metric tons in 2050. Next, we look at the LEENA case. It is based on 5 areas of disruptive innovations in clean consumption technologies for edge node devices and power distribution architectures. In the LEENA case, energy efficiency of a device is based on scientific, verifiable concepts of useful work. Extensive research in energy efficiency and useful work based on real products we use every day helped us identify 5 primary areas where we can eliminate energy waste. These areas are improved system and device edge node architectures, use and development of modern technology in product design, eliminating unreasonable design constraints, development of architectural and technology-independent energy policies and regulations, and finally, support for complete visibility and transparency of energy data. Before we examine some simple examples of these primary areas of energy waste, let's define what we mean by useful work. Energy efficiency is a heavily overloaded term. In marketing, it is used to compare products or services to each other or an arbitrary baseline. Unfortunately, it is often used to convey meaning based on divergent constituent concepts. When used as an adjective, it often lacks sufficient context to lead to an understanding of the subject of the term, beyond implying a vague value proposition. Like attributes such as natural, healthy, green, organic, sustainable, ethical, and eco-friendly, the term energy efficiency is often abused to imply a qualitative value that is deceptive. In the forum, we base our definition of energy efficiency as a simple quantitative ratio of useful work performed by a system divided by the energy consumed by the system. This ensures our calculations of energy efficiency are verifiable and both technology and architecturally independent. This is a key concept that allows us to strip away all of the marketing hype and false claims made by product manufacturers. Let's look at some examples. The first area of disruptive innovation we consider is the need for improved system and device node architectures. From an energy perspective, the system design of most products we use is extremely poor and combined accounts for as much as 25% of our total energy waste. Unfortunately, when products are designed and energy efficiency is not included as an intended consequence of the design, energy waste will be a result. A modern garage door opener is a wonderful example of excellent mechanical design and extremely poor system design. Simple products like garage door openers waste as much as 95% of the energy they consume. The diagram on the right illustrates a simple block diagram of an IoT-connected garage door opener. By instrumenting each of these major elements in the garage door opener, we can directly measure and evaluate the power consumed by these subsystems. From the intended purpose of a system, we can calculate the energy required to perform useful work. This slide is a simple list of useful work performed by a typical automatic garage door opener. Opening and closing the door on command is its primary intended purpose, but it also must do so safely, in a reasonable time frame, be remotely controlled by an approaching vehicle or keypads located in the garage or outside in the yard. It may also be convenient to connect to other systems that provide advanced IoT features to allow remote status monitoring and support control by connected devices such as phones and computers. This chart illustrates the energy consumed in joules, which is equivalent to 1 watt per second, for an automatic garage door opener. The red line illustrates the energy consumption of a conventional garage door opener, raising and lowering a 150-pound door. The green line illustrates the energy consumption of a LEENA architecture, and the yellow line illustrates the calculated useful work performed by the garage door as an edge node system. It is interesting to note in a conventional design, energy consumed to raise and lower the garage door is less than the energy consumed by the light, the idle state, or to support IoT functionality. In this example, the energy efficiency of a conventional design is just 2.5%, with energy waste of over 100 kilowatt hours per year. In the LEENA design, energy waste is reduced to under 4 kilowatt hours per year. This means the 150 million conventional automatic garage door openers in the United States waste 15.27 billion kilowatt hours of electricity each year, cost consumers $2.55 billion, and generate over 11,362 metric tons of greenhouse gas equivalent CO2 pollution, all for energy waste. The second area of clean consumption technology we consider is the use and development of modern technology in product design. Often to save pennies in bill of material costs, manufacturers use inferior technology, accounting for as much as 15% of our overall energy waste. An example of this is continued use of split-C transformers in low-voltage AC power systems. In the United States, over 380 million split-C transformers are currently connected to centralized AC power grids to power residential doorbells, thermostats, sprinkler controllers, and outdoor lighting. Yet much more energy-efficient options have been available for many years. The split-C transformer was initially designed and put into production in the 1880s. The static load of a typical split-C transformer is about 1.25 joules, which consumes 10.95 kilowatt hours per year of electricity. In 2018, the 380 million split-C transformers in use in the United States accounted for 4.16 billion kilowatt hours of energy waste, cost consumers over $694 million per year, and generated almost 3.1 billion metric tons of greenhouse gas equivalent CO2 pollution. By replacing 19th century technology with 21st century AC power sampling technology, each year we can reduce the load on the power grid by over 4 billion kilowatt hours per year, save consumers over $680 million, and eliminate over 3 billion metric tons of greenhouse gas equivalent CO2 pollution. The energy efficiency of split-C transformers used in these applications is just 0.4%, which of course means 99.6% of the energy consumed by these transformers is energy waste. Compliance with unreasonable design constraints is our third area of concern and is responsible for as much as 35% of our total energy waste. The LEENA Home and LEENA Hybrid home architectures were developed to eliminate the biggest contributors to this energy waste: use of alternating current as the primary power source for edge node devices. The war of currents in the 19th century established benefits of AC power distribution for centralized power grids. So today, all power distribution is based on alternating current. The photo in the upper left corner of this slide shows what AC power distribution in New York looked like in the 19th century. The middle photo shows modern AC power distribution in the 21st century. Transformers upconvert AC power to hundreds of thousands of volts to minimize IR losses in transmission of power over long distances. The photo on the right side of the slide illustrates what modern 21st century DC power distribution looks like in our homes to power edge node devices. Manufacturers of modern low-power devices often purchase off-the-shelf AC to DC power converters like the one shown in the photograph. Because the cost of power converters is often more important to manufacturer profitability than the efficiency of the converter, low-cost, low-efficiency converters are sold with products. When all the devices connected to the AC to DC converters shown in this photograph are disconnected from the devices they power, the static load of these power converters is 13.2 watts. Therefore, the static load of this power strip is over 115 kilowatt hours per year. Worse yet, the average efficiency of these converters is about 60% when used to power devices, which means even more energy is wasted. LEENA architectures supply DC power directly to edge node devices, so no AC to DC conversion is necessary. As we complete the second decade of the 21st century, the Internet of Things is promoted as an important element of our clean energy future. IoT devices marked as smart devices claim they will not only make your life easier, but will save you energy. But powering these devices takes energy, and because most of these devices are controlled remotely and are on 24 hours a day, they consume considerably more energy than they save. A simple example of a typical IoT architecture is to use a Wi-Fi connected power switch to automate a 60-watt LED light fixture controlled by a smart device with voice recognition. The load of the LED light is 9 joules, so if the light's on for 2 hours, it consumes 18 watt-hours per day. The Wi-Fi connected power switch consumes 17.8 watt-hours per day, 0.7 watts when the light is off, and 1.2 watts when the light is on. Unlike conventional LED lights, the LEENA architecture powers the LED array with DC power, eliminating the internal AC to DC converter used in all modern LED light bulbs. This reduces the power load from 9 watts to 6 watts per hour. The Wi-Fi power switch is also not required, saving an additional 17.56 watts. It also does not require a Wi-Fi connected IoT controller. Therefore, the LEENA IoT architecture, based on DC power distribution, consumes only 1/3 of the power consumed by a conventional IoT AC design. And because the light bulb does not need an internal AC to DC converter, the LEENA design also consumes only 2/3 of the power consumed by a conventional AC-powered LED light controlled by a manual switch. With the LEENA architecture, voice control of the light is also local to your home, eliminating power consumed by internet traffic and data piracy concerns related to data harvesting by thousands of internet-based data farms. The fourth area of concern is the need to write energy policies and regulations that are technology and architecturally independent. Poorly written policies and regulations account for 15% of our overall energy waste. As layers of policies and regulations become more specific, they often become unintentionally restrictive, and within the regulatory framework of an architecture that, for the past 120 years, has dominated energy markets, seemingly harmless regulations establish barriers to use of disruptive innovations in energy technologies and architectures. Innovations always outpace regulations. Therefore, policies and regulations that are architecturally or technology dependent often prolong use of inferior technology well beyond their useful life or best used by date. So, it should not be a surprise energy policies and regulations both assume and mandate continued use of centralized grid-supplied AC power. For example, in California, it is illegal to build a house or commercial building with solar cells that are not connected to a centralized power grid. So entrenched is the concept of centralized distribution of power, the term most often used in the power industry when someone disconnects from the grid is grid defection, implying bad behavior. Under current law, residential solar systems in California must meet the requirements of Title 24 of the California Code of Regulations, applicable health and safety standards and requirements of state and local permitting authorities, applicable rules of the California Public Utilities Commission regarding safety and reliability, and the safety and performance standards of the Institute of Electrical and Electronic Engineers and accredited testing laboratories such as the Underwriters Laboratory. In California, Title 24 specifies solar energy systems comply with the Energy Code. And the Energy Code specifies for single-family homes, solar installations must be connected to the grid at the main service panel. This is interpreted to mean all solar installations must connect to a centralized power grid where it is monitored and controlled by a centralized authority. So if the utility power goes down, your solar power does as well. Not an ideal architecture. A typical AC to DC solar inverter running at full capacity is about 95% efficient. However, they normally run at a lower power capacity, so the effective efficiency is around 92%. Converting AC power back to DC power to be used by edge node devices is on average 70% efficient. Therefore, conversion efficiency from DC to AC back to DC results in an efficiency of 64%, or a loss of 36% in energy waste of the power produced by your solar panels. Finally, let's examine how energy efficiency and consumption data is provided to consumers. This accounts for 10% of our total energy waste. How much energy do the dozens of products you use every day actually consume? How efficient are they? These are questions most people never ask, and if you ask, you often find it very difficult to get answers. In fact, these are questions both industry and government don't want you to ask. Industry wants you to trust them and assume the products you purchase are manufactured with the latest energy efficient technology. Government wants you to trust them and assume they are developing policies and regulations that eliminate your need to worry about such things. As consumers, we need to break the cycle of passive acceptance of the notion that energy efficiency is a complex concept that should be left to the professionals. The most powerful motivation for industry to build and regulators to require energy efficient products is for consumers to make it clear they value energy efficiency. Even with the best of intentions, the way energy data is presented is often unintentionally misleading. For example, in 2018, Energy.gov released 2 back-to-back Fact of the Week publications. From these publications, you may get the impression an electric vehicle is 3 to 6 times more energy efficient than a conventional internal combustion vehicle. But like most facts related to energy efficiency, these facts lack sufficient context to separate fact from fiction. You may assume because these facts, published in the summer of 2018, are representative of vehicles today, but you would be wrong. The source data in these articles compare the average of over 100 internal combustion vehicles tested in 2013 to a single electric vehicle tested in 2012. Also, a more relevant measure of energy efficiency is not from the primary fuel source to the road as presented in these articles, but from the earth to the road. We updated the Energy.gov fact sheets to include 2018 earth to primary fuel efficiency data from the EPA, EIA, and DOE, and added 2 additional vehicle types, gas-electric hybrids and fuel cell vehicles. This chart summarizes a more accurate comparison between vehicle types. According to DOE, the efficiency of petroleum production from crude oil to gasoline is 91.4%. An additional 3% is lost in transport, so the earth-to-fuel efficiency for gasoline is 88.4%. According to EIA, the efficiency of earth-to-grid delivered electricity in 2018 is 33.7%. Gas-electric hybrid vehicles convert gas to electricity and consume electricity in the same way plug-in electric vehicles do. They also harvest electricity from regenerative braking, So secondary fuel, which is gasoline, efficiency conversion to primary fuel, which is electricity, is 45%. Primary fuel to road, according to energy.gov, is 82%. Therefore, earth-to-road efficiency is 32.6%. Plug-in electric vehicle fuel-to-road efficiency is 82%, but earth-to-fuel efficiency is 33.7%. Therefore, earth-to-road efficiency is 27.6%. Internal combustion vehicles' earth-to-fuel efficiency is 88.4%, but fuel-to-road is only 30%. Therefore, the combined efficiency of earth-to-road is 26.5%. Fuel cell vehicles use electricity with an efficiency of 33.7% at hydrogen generation facilities. Conversion efficiency from electric to hydrogen at these facilities is 73%. Conversion from hydrogen back to electricity to charge the batteries in a fuel cell vehicle, which for all practical purposes is an electric vehicle, is 60%. So secondary fuel, which is electricity, to primary fuel, which is also electricity, is 43.8%. Recovered electricity to road is 82%. Therefore, fuel cell vehicle earth-to-road efficiency is 33.7% times 43.8% times 82%, which is a combined earth-to-road efficiency of 12.1%. To calculate the fuel cost in 2018, we use a rate structure of $3 per gallon of gasoline, 16.7 cents per kilowatt hour of electricity, and $12.50 for a kilogram of hydrogen. To calculate the greenhouse gas CO2 pollution per mile, we use EPA data of 8.81 kilograms per gallon of gasoline and 0.744 kilograms per kilowatt hour of electricity. Surprisingly, in 2018, hybrid vehicles produce significantly less pollution than any other vehicle type. Also, in 2018, plug-in electric vehicles are not sufficiently cleaner than new internal combustion vehicles. But perhaps the most surprising fact is grid-based fuel cell vehicles produce twice the pollution and are significantly more expensive to run than any other vehicle type. So complete visibility and transparency of energy data is critical to understanding how energy efficiency impacts us. This analysis is based on centralized grid-supplied electricity. The good news for plug-in electric vehicles is that electricity from distributed sources such as rooftop solar substantially reduce primary fuel costs and eliminates virtually all greenhouse gas equivalent CO2 pollution from plug-in electric vehicles. Let's look at another example where context is important to understand energy data. The Energy Start program publishes test methodology and certifies energy guide labels to help consumers compare products based on energy consumption. In 2015, I purchased a television based on reviews from CNET and the energy guide label shown on the right side of this slide. I was pleased to find out one of the highest rated 4K Ultra HD televisions was significantly more energy efficient than similar television tested for the Energy Start program. In bold print, the energy guide label for this television estimated the yearly energy cost to run this TV is only $18 per year. In very small print at the bottom of the label is an estimate that the annual consumption of energy for this TV is 164 kilowatt hours per year. That corresponds to an active load of 90 joules. When I got the television home, I measured the actual load and discovered the following. The energy load was 225 joules, not 90 joules. Like most modern TVs, this one has 6 picture modes. It powers up in the calibrated mode, which is the default mode most people use because it is adjusted for the best picture. The vivid mode consumes 250 joules and is normally only used in stores because it has the best display in high ambient light. The standard mode is only used for testing and exploits poorly written and enforced consumer product testing requirements that allow manufacturers to define a standard mode of operation that turns off all processing that is not absolutely required to display video. such as gamma correction, jitter suppression, upconversion, backlighting, and other processes that improve picture quality. If you think this is deceptive, it is, and yet fully supported by Energy Star guidelines. This is how energy consumption was calculated for the Energy Guide label, based on the special standard mode with a picture so bad it is almost unwatchable. Also, the annual consumption of this TV should be listed at 410, not 164 kilowatt hours per year. And if you lived in San Diego in 2015, your electric rate was 18 cents, not 11 cents per kilowatt hour. This is how the estimated yearly energy cost for residents of San Diego should have been calculated. So the actual cost to run this television in 2015 was $74, not $18. Today, in 2018, the electric rate for residential service in San Diego is 24.7 cents per kilowatt hour. So the real cost of running this television in San Diego in 2018 is $101 per year, over 5 times the annual energy estimate cost highlighted in the energy label just 3 years ago. Now let's look deeper into how energy data is provided to help us purchase products that are more energy efficient. Let's examine Energy Guide labels from the United States, Canada, and Europe. Only the Energy Guide label used in the United States highlights or features an estimated yearly energy cost on its label. This allows customers to quickly compare products based on operating costs without actually doing the math or being concerned about electric rates, or understanding in 2018 electric rates in the United States varied from 8.5 to 45 cents per kilowatt hour. Therefore, depending on where you live, the estimated yearly energy cost for the product shown in this label varies from as low as $50 or as high as $263 per year. The structure of this label also implies that at $70 per year, this product is in the mid-range of similar products, although in fine print it does state cost range is not available. This label also includes an estimated yearly electric use of 585 kilowatt hours per year as a secondary measure of efficiency. The Energy Guide label from Canada is a bit better because it highlights the actual energy consumption of the product rather than an arbitrary estimate of operating cost. This Energy Guide label also includes a chart that compares this product with energy consumption data from similar products to allow consumers to quickly understand how the energy efficiency of this product compares to products with similar features. In fact, the chart shows this product uses less than any other product with comparable features tested under the Energy Star program. Labels used in the European Union are also different. Featured on the label is a rating from A++, the highest rated products for energy efficiency, to D for the lowest rated products. Below the featured graphics is listed the annual energy consumption in kilowatt hours per year. Studies in Europe confirm 83% of the time consumers make purchase decisions based only on the featured rating of similar products, regardless of the actual energy consumption of the product. This means a product with an A++ rating would be considered more environmentally friendly and selected 83% of the time over a product with a B rating, even though it may, as in this case, consume significantly more energy. The term energy efficiency fallacy is when primary data, which is the data highlighted on a label, conflicts with secondary data. Primary data is most often the determining factor when considering purchase decisions. The term energy efficiency fallacy is when primary data, which is the data highlighted on a label, conflicts with secondary data. Primary data is most often the determining factor when considering a purchase decision. As you may have already guessed, all 4 labels on this slide are for exactly the same product. Of course, the energy consumption of this product in Canada is not 28% lower than it is in the United States. Canada, Europe, and the United States use different test criteria to measure consumption. At this point, you may wonder why we focus so heavily on government publications and Energy Guide labeling. Simple. Government agencies at least attempt to provide consumers meaningful energy consumption data. This is in stark contrast to the complete absence of any meaningful data provided by product manufacturers. The LEENA Forum advocates for all products to disclose on websites and at the point of purchase energy efficiency data based on well-defined standards of useful work, not arbitrary standard mode test methodologies that change from year to year and region to region. In the next series of slides, we first examine the impact of the LEENA architecture on centralized grid-based supply and demand, and then drill down into the expected impact on residential markets for grid-supplied electricity. We saw this slide a few minutes ago. It illustrates real-world EIA data and analytics for the balance between electrical energy supply and demand for delivered electricity in 2017. It is clear from this illustration we have a problem. According to publications from the energy industry and virtually all government agencies, the solution is simple. We need to replace carbon-based fuels quad for quad with renewable energy sources such as wind and solar as quickly as possible. At the Forum, we see the problem differently. We know that for every unit of energy we don't consume on the demand side, we reduce the amount of energy we need to harvest by a factor of 3 on the supply side. Therefore, reducing a unit of energy on the demand side has the same net impact on our environment as replacing 3 units of carbon-based energy with 3 units of renewable energy on the supply side. To help illustrate the impact of eliminating energy waste from edge node devices, we simply replace the sphere that represents energy delivered with 2 spheres, one that represents 20% of the energy that performs useful work, and one that represents 80% of the delivered energy that is consumed as energy waste. Next, because we understand we cannot eliminate all energy waste on the demand side, we reserve 20% of the overall energy demand to account for energy waste in products that perform useful work. This means we can target 60% of the delivered energy that is excess energy waste. Now we can mirror what we did on the demand side of the balance beam on the supply side. Finally, we target eliminating the excess waste on the energy demand side, which allows us to eliminate 60% of the total energy harvested from the Earth on the supply side. This leaves us with some pretty remarkable results. Energy efficiency has increased from 33.7 to 50%, as expected. The energy consumed is reduced from 12.67 to 5.07 quads, which reduces energy harvested from the Earth from 37.25 to 10.14 quads. The amount of energy produced from renewable sources remains the same as in the EIA reference model case, at 691 billion kilowatt hours per year. But the amount of energy that must be delivered to consumers to meet energy demand decreases from 4,042 billion kilowatt hours a year to just 1,617 billion kilowatt hours per year. Therefore, the percentage of renewable energy increases from 17.1% to 42.7%. Also, greenhouse gas equivalent CO2 pollution is reduced from 1.76 billion metric tons to just over 480 million metric tons. If we apply this model to the EIA reference model projections for 2050, the results are even more remarkable. This slide we have also seen before. It represents EIA reference case predictions of energy consumption for delivered electricity in 2050. This reference case includes investment of trillions of dollars to replace carbon-based fuels with renewable energy sources, with the disappointing results of less than 1/3 of our energy coming from renewable energy sources. In 2050, with the LEENA case, we maintain a 50% ratio between useful work and energy waste on both sides of supply and demand. Therefore, in 2050, energy consumption drops from 15.07 to just 6.03 quads, and total energy harvested from the Earth drops from 40.76 to only 12.06 quads. Even more impressive, we assume continued development of renewable energy, so it remains at 1,651 billion kilowatt hours as in the EIA reference model. But the delivered energy drops from 5,255 to 1,617 billion kilowatt hours per year. This means we produce over 100% of the energy needed to supply electricity in 2050 with renewable energy sources, completely eliminating greenhouse gas equivalent CO2 pollution from carbon-based fuels. In the next series of charts, we examine the impact of the LEENA case on grid-supplied residential electricity. Based on AEO 2018 data, this chart illustrates projected residential electric use from 2017 through 2050. In addition to the reference case, we include the $25 carbon allowance fee case and new efficiency case. It is noteworthy that in all three cases, total demand for residential electricity continues to increase through 2050, with the highest energy demand for the reference case, shown in blue, and the lowest energy demand for the $25 carbon allowance fee case, shown in orange. Also illustrated on this chart is the projected amount of electricity generated from all renewable sources for grid-based delivery of residential electricity. In all three cases, generation from renewable energy sources is projected to increase from 53 to over 760 billion kilowatt hours by 2050. By adding the LEENA case to this model, we see a significant drop in residential demand for electricity. In fact, our model indicates by 2045, the amount of electricity generated from renewable sources will actually exceed total demand. This chart illustrates the projected baseline cost of residential electricity from 2017 through 2050. The reference case and new energy efficiency case are virtually identical, with cost increasing from 12.67 cents to just under 30 cents per kilowatt hour in 2050. In the $25 carbon allowance fee case, residential consumers should expect to pay over 36 cents per kilowatt hour. Now, most of us that actually pay our electric bills may feel the baseline cost of residential electricity was significantly higher than 12.67 cents per kilowatt hour in 2017. In reality, the baseline cost of electricity varies by a factor of 5 for different areas of the country. And with the move from tiered rates to time of use rates, variations up to 4 times the base rate are possible in 2050. Therefore, under all cases, it is possible you will see rates in some communities exceeding $1 per kilowatt hour. But for the purposes of our analysis of the LEENA case, we will use the EIA calculated national baseline rates. When we update this chart to include the LEENA case, we see a significant drop in the cost of residential electricity as homes are converted to LEENA Home and LEENA hybrid home architectures, and as energy efficient LEENA edge node devices replace older, less efficient devices. The cost of grid-based electricity, like all commodities, is subject to supply and demand. The LEENA case eliminates 60% of the residential electricity demand for grid-based residences and 100% of the demand from decentralized off-grid architectures in suburban and rural communities. In this chart, we combined the two previous charts to determine the annual projected cost to residential consumers for grid-supplied electricity. For all cases in 2017, the cost of residential electricity was $174 billion. The most expensive case for consumers in 2050 is the $25 carbon allowance fee case, which, despite the lowest energy consumption, increases to $532 billion. Adding the LEENA case to this model, we see by 2050 the annual cost for grid-supplied electricity for residential consumers drops significantly. In fact, by 2050, total cost to consumers is less than 10% of the projected cost in the $25 carbon allowance fee case. To better understand the impact of the LEENA case on the economy, if we compare the $25 carbon allowance fee case to the LEENA case for the total cost paid by residential consumers each year from 2020 through 2050, with the LEENA case, residential consumers save over $7.7 trillion. Although total savings over the $25 carbon allowance fee case are less in commercial, industrial, and transportation sectors, the total reduction in cost savings with the LEENA architecture exceed $18 trillion. In our final set of charts, we examine the projected greenhouse gas equivalent CO2 pollution for the three primary EIA case scenarios for production of residential electricity. The red line indicates a dramatic reduction in greenhouse gas equivalent CO2 emissions beginning in 2020 as the $25 carbon allowance fee case pressures carbon-based energy producers pay billions of dollars to continue to operate. It is currently unclear what this money will be used for, but likely these costs will be passed on to consumers. By 2050, EIA models predict for the $25 carbon allowance fee case, carbon emissions will be reduced by 77% over the baseline reference model. This is impressive, but as we've seen, this will ultimately cost residential consumers trillions of dollars and will still fail to eliminate carbon-based fuels used to power residential consumers. When we add the LEENA case to this chart, we see over time the LEENA case actually eliminates more greenhouse gas equivalent CO2 emissions than the $25 carbon allowance fee case, and by 2045 completely eliminates greenhouse gas CO2 emissions from production of residential electricity. This slide illustrates the structure of the forum. Our plan is to launch the forum in the first quarter of calendar year 2019, and within 9 months, staff officer and board of director positions, complete peer reviews and begin publishing research findings, file key patents and trademarks, and work with EIA in formal development of the LEENA architecture and the LEENA case for inclusion in AEO 2020 release. We plan to establish the Regulatory Advisory Committee and begin work on guidelines to review policies and regulatory standards to ensure future standards will be technology and architecturally independent. We will establish and staff the Architectural Committee and complete and publish architectures for the LEENA Home and LEENA Hybrid Home. Staff the Advanced Technology Committee and begin component development in key power conversion technologies and LEENA comms. Staff the Communications Committee and publish the IoT protocol stack, communication chip requirement documents, and select vendors for chip development. Staff the Energy Efficiency Committee and publish useful work standards and guidelines for laboratory testing of edge node devices. Staff the Host Platform Committee and complete requirements and begin evaluation of secure operating systems and database structures. Also begin development of dashboards and user host interfaces. You take just one thing away from this presentation. I hope it is a better understanding of the importance of energy efficiency on our energy future, as well as on our economic and environmental future. And take the opportunity before you to join the forum and become an important part of a comprehensive solution to the energy crisis. Keep in mind, the cleanest energy is energy you do not use. It does not need to be harvested, distributed, purchased, or consumed. Change is hard and often initially very unpopular because it challenges our understanding of the world. It is often the case when disruptive innovations in technology are first proposed, they're attacked by established institutions with a vested interest in opposing or delaying change. But over time, the best innovations succeed and change follows. Keep in mind, Pythagoras proved the earth was round in the 5th century BC, but for the next 1,000 years, academic, religious, and government institutions claimed the earth was flat. They were wrong. In 1981, IBM, the largest high-tech company in the world, published a marketing report claiming the market for personal computers was as large as 250,000 units, and primarily users would be accountants running VisiCalc. They were wrong. In 1991, Motorola, inventors of the cell phone, published a marketing report claiming the market for cell phones was as large as 1 million users and would primarily be salesmen in urban areas. They were wrong. In 2010, Cable Labs published a marketing report claiming video streaming was a novelty that would never challenge cable companies. They were wrong. For the past 50 years, we've been told the answer to the energy crisis and global warming is to replace quad-for-quad carbon-based fuels with clean energy technologies. They are wrong. Clean energy technologies on their own will not solve the energy crisis. The real solution requires development of both clean energy and clean consumption technologies. The choices we make today will determine which world we live in tomorrow. You can find more information on the LEENA Forum by going to our website at leenaforum.org or contact Robert Schutz at LEENA Laboratories at the email address shown on this slide. Thank you for viewing this presentation, and we look forward to hearing from you. Have a great day.